Hello everyone, welcome to another RUS demonstration, RUS webinar. Today we will have a case study over Mexico City studying the land subsidence with Sentinel-1. This event is happening due to the Copernicus Eyes on Earth Roadshow, which is the 4th edition, which was supposed to happen in Bucharest, but due to the current situation, it has been cancelled. So I will now give the word to Martijn, who is responsible for the show, so that he will explain you a bit more about it.
Yeah, Georgia, thank you very much. My name is Martijn Seiger, and I'm the project lead of the Eyes on Earth consortium. And I will share my screen with you. The Eyes on Earth Roadshow, it would have been the 4th edition in Bucharest today and tomorrow. Unfortunately, for obvious reasons, this cannot take place. However, we have, I will give you an online insight in the roadshow as we have done it in 2019. So what's the target? What are our goals? Well, we learned from the experience we have that for the dissemination of space data, and especially on the application side, a lot of work has to be done. Not only by informing the experts about real-life problems people are facing, how to use space data sets, but also to inform the non-usual target audience about which specific training tools are already available. Then also Copernicus also has a lot of programs supporting the uptake of data and initiatives to use the Copernicus data more and other space data sets in collaboration with other geospatial data. So how do you develop a business and how do you develop yourself? Which kind of skills do you need to work with spatial data, including Copernicus data? There's also a lot of information products are also available already. However, how to access this, it's also not quite well known. So we have an obligation to inform the people on this. And especially also it's an interaction from a technology transfer point of view. There has to be a collaboration between professionals, professors and students to utilize all the knowledge and to exert this into valuable products which can benefit our society. We also want to raise awareness for societal challenges and boost the spin-offs of universities, but also from other companies, for example. That's why we took the payoff of the roadshow Inspire, Explore, Act. So the inspiration part is on to inform the audience and the participants on what kind of businesses or societal challenges could I solve when using space data. The exploration phase is how does the value chain look like and where am I in this value chain? Do I know which kind of skill set I need to be operating in this interesting field of expertise? And also the act part is very important for us because acting is also learning and doing. So what kind of people do I need to help me and to solve the challenges I face? To give you some impression on how a physical event would have looked like, and which we will organize, I hope very soon, but you have to be realistic. These are some impressions from the events in 2019. So there are many people on the slide, so it's a real event. And maybe some of you will know some of the faces, but there are people from the entrusted entities, which are relevant players in the Copernicus domain. There are also partners from the DIAS who will present their DIAS and how to access it, for example. And we also have organized a market fair in which people can meet, create new ideas, and inspire each other. We hope this will be done also online. So please use your social media channels to reach out. For more information on the actual events, how it took place last year, These are the links for YouTube, so you can visit it and have some feedback of participants and on hosting companies, for example, Eumetsat, who will give their view on the roadshow. And then for the 2020, well, today we have this land subsidence mapping using Sentinel-1 in collaboration with Copernicus RUS. And in June 2020, we're still planning to have the event in Croatia. However, not only Corona, but also an earthquake took place over there. So it's quite challenging. So maybe the setup will be a little bit converted. If you have any good ideas, feel free to reach out. So don't hesitate on this. So I'll leave it from here, because before you dive in the content, I can only say enjoy the training and really looking forward to meet you offline. Below my contact details, do not hesitate to reach out. Enjoy the training, and a very special thanks to the Copernicus RUS team for facilitating this. Bye-bye.
Okay, thank you very much, Martijn. So now just give me a second so that I move to the presentation and that we start the demonstration. Okay, so in this demonstration, we will learn how to use SAR interferometry to identify and map land subsidence using the ESA SNAP Sentinel-1 toolbox. We will talk a bit about the study area, the Sentinel-1 constellation, the RUS service. Then we will continue to the exercise in RUS virtual machine. We will have the take-home message and a Q&A session will follow. The webinar will last around 1.5 hours. And please note that it is advisable to start sending us your questions immediately as soon as you have one and throughout the demonstration. My colleagues will assist answering to as many of your questions as possible so that we will not have too many questions accumulated for the Q&A session. Now let's have a look to our study area, which is the Mexico City. The land subsidence in Mexico City is caused by groundwater overexploitation. The city is partially built on the area of a former lake. It rests on the heavily saturated clay, which is collapsing due to the over-extraction of groundwater. Here we can see a model of how this mechanism works. Over the last century, the subsidence of the area has been more than 9 meters, resulting in damages to buildings, streets, sidewalks, sewers, stormwater drains, and other infrastructure. Previous studies of SAR interferometry using ERS data showed a maximum subsidence rate larger than 30 centimeters per year over parts of the city. Current subsidence rates using Sentinel-1 SAR data approximate 2.5 centimeters per month. Now let's see quickly some information about the Sentinel-1 data we will use. In this exercise, we will be using SAR data provided by the Sentinel-1A satellite. The Sentinel satellites are included in the space component of the Copernicus program of the European Commission and the European Space Agency. The Sentinel-1 mission is formed by a constellation of 2 twin satellites faced at 180 degrees to each other. It is an active sensor working on C-band. It includes a right-looking active phased array antenna providing fast scanning in elevation and azimuth, and it also provides data with a short repeat cycle of 6 days and with different imaging modes. Here you can see the 4 different acquisition modes, of which we will use the IW, which is meant for land applications, and also the 4 products of each mode. Of each we will use SLC, since it contains complex data of amplitude and phase that is necessary for interferometric processing. In the next slide, you can see the 3 subswaths, the interferometric wide swath, and the 9 bursts of each subswath. But let's talk a bit more about interferometry. When we obtain 2 radar images over the same area that are of the same orbit and have the same geometry, we can create an interferogram, which represents the deformation between 2 SAR acquisitions by calculating the phase difference of those 2 products. The interferometric phase consists of fringes, and one full color cycle has values from minus 3.14 to plus 3.14. With interferometric processing, we can also obtain information about the coherence of two images. This means how well correlated is each pixel of the slave image to the corresponding to the master image pixel. The closer to 1 the value is, the more coherent the images are. Finally, after we have created our interferogram and applied all necessary steps, we can unwrap the face. Now let's continue to some information about RUS service. RUS stands for Research and User Support for Sentinel Core Products. It is an initiative funded by the European Commission and managed by ESA, with the objective to promote the uptake of Copernicus Sentinel data and support research and development activities. The service provides a free and open scalable platform in a powerful computing environment, hosting a suite of open source toolboxes pre-installed on virtual machines, which allow you to handle and process the data derived from the Sentinel satellites. What does this mean? Well, with a large amount of the data produced by the Sentinel satellites, the challenge is no longer the data availability, but rather storage and processing capacity. To solve that, RUS offers virtual machines so that you have the appropriate computing environment to handle the data. In addition to all that, RUS also provides a specialized user help desk to support your remote sensing activities with Sentinel data and a dedicated training program. You can find all the information about the project and how to register on our websites, so I recommend you to check them after the webinar to get familiar with the service and see the VM specifications, list of software, etc. I will quickly show you those websites before we start the exercise. So we also have a YouTube channel where you can find all the videos of our previous webinars, and you will also find this one in a few days. Now, just let me show you very quickly all the processing steps that we will perform. First, we will create some graphs. In the first one, we will insert the first of the two products that we will have downloaded. The first thing we will do is to split it, because we will need to select which subswath our area belongs to and which are the bursts that we will use. I will explain you later once we will be in the virtual machine. Next, we will apply the orbits, which is actually this processor. With this processor, we can have accurate satellite position and velocity information. So based on this information, the orbit state vectors in the abstract metadata of the product are updated. Usually they are available a few days after the product is released. When we will create this graph, we will use the batch processing option so that all these 4 steps will be applied for both products just with one go. The final product, the right, will contain the information of both the split product and the updated orbits. And why we do that, why we create graphs, is because we want to save some storage space, and this way only the last product is physically saved. So after we will apply this one, we will take the 2 products that will be the outputs of the right of the previous one, and we will continue to the co-registration. What is co-registration? Is actually putting the 2 images together. I will explain a bit more later. The co-registration consists of 2 steps. The first one is the back geocoding. It actually co-registers the 2 images, the master and the slave, on the same subswath using the orbits of the 2 products and the digital elevation model. After this one, the enhanced spectral diversity is following. It is exploiting the data at the overlapped area of the adjacent bursts and then performs rates and azimuth correction for every burst. Then we will continue with the creation and the formation of the interferogram. Then we will apply the deburst operator, which is actually to remove this black part which is between the two bursts. And then we will write this output. After we will create this one, the read product will be the write of the previous one, and we will apply the topographic phase removal operator. We will remove the phase due to topography. Then we will apply the multi-looking one, because the original SAR image contains some inherent speckle noise, and this processing is applied to reduce the speckle appearance and to improve the image interpretability. So we want to obtain at the end square pixels. The next one will be to use the phase filtering in order to reduce the phase noise. This is also useful for the phase unwrapping. And then we will write one product which will contain all of those steps. And we will add another operator, which is the snafu export, so that we will export what we need for the phase unwrapping that is coming afterwards. The next steps we will apply is the phase unwrapping, that we will do it using the terminal in our virtual machine. Then this result we will import it in Snap using snafu import. We will calculate the displacement of the area. Then we will apply the geocoding operator. It's the terrain correction one, which convert the radar coordinates into geographic coordinates. And what we will do afterwards is we will use the stack operator, where we will have the information of the terrain corrected product and of the displacement. So we will take the information of those two SAR products and we will put them together in one. I will also show you how to mask the coherence, because if we have some very low values of coherence, we would like to remove them. And then show you how to export the data for further processing and use, either to QGIS or to Google Earth. Okay, now let me show you a bit our websites. This one is the RUS training website, where we have all our material and all the trainings. So here, if you go to the training upcoming, you can see all the upcoming trainings that we have planned, and also you can go to the past one and watch, for example, the previous webinar we had last month. You can go here, you can find the video and also a Q&A document. You can also go to the e-learning and practice in the courses we have already uploaded. The other website we have is the RUS portal, the rus-copernicus.eu. So here you can come and you can create an account. You can navigate to see the RUS offer and the RUS service. If you go to the RUS library under Learn by Yourself and you go to the RUS lectures tab, you can find all the tutorials we have available. Last one, I will show you the YouTube channel that you can see we have all the videos of all the previous webinars we have created. So if we go back to this one, if we click here, login, register, once we have created our account, we just go here and we log in. I have my credentials saved. And here you have this interface. So if you go to your dashboard, you can click here, request a new user service, and you can request for a virtual machine. So once you have requested, you will see this table that appears down here that will refer to your virtual machine. And you can go here, click access my virtual machines and just access it. So this is exactly what I did. And when you do that, you get redirected to another window where you insert your credentials of your virtual machine and you just log in. So once you're in, you see that this is how it looks like. You have here all the software pre-installed, the free software that are provided with the creation of the virtual machine. So before we start the exercise, just give me a minute to make the full screen mode. Okay, so the first thing we need to do before we start the exercise is to download our data. So once you click here on the Firefox, you can see immediately that the Open Access Hub tab is being opened, where you go here in the Open Hub, you click, and you can navigate, you create an account, and you can download the data. Also here you have the RUS user forum. If you have any questions, you can post them here and you will get an answer from someone who can help you. Or if you can help someone else, you can do the same as well. So let's go here to the Open Access Hub. So if we click in the Open Hub, I have already opened it. So we have it here. We just go here in the Mexico City area. We navigate and we create this small rectangle. So once we do that, we go here on the left on the options and we select as sensing period 6th June of 2016 as the start and an end day. We need two products. The second one is acquired on September 10th of 2016. So let's search first for the first one. Once we insert the sensing period, we select the mission Sentinel-1. From product type, from all the options we have, we select SLC, and from all the sensor modes, we select IW. And then we click search. And here you can see that this product is found and it's, this product is found and is here. So here on the left, here you have the product. You can go here to click download product. I would like also to inform you that here you can see that this product is offline. So currently every product that is older than 1 year from today's day, every day, it goes offline. So the way to download it is to make it online. Once you click here and you try to download it, you receive this message, offline product retrieval initiated, and in a few minutes it is available. And then it remains online for 4 days so that other people can also download it. Just to let you know that with your account, you cannot request for more than one product every 30 minutes. So in this case, okay, we just click OK. It goes immediately in the cart. Here you can see we have the cart. So when the product is available, unfortunately, you don't receive a message. So you have to go every now and then in your cart. And you can see here that our product is added. Once it is online, this gray area will become white. So if you go back again to the search and you insert here September 10th of 2016 in both fields, you will search and you will have the second product as well. Okay, now we have downloaded our products and you can copy them, you can move them to the folder you wish. Let me close that. So if you go here and you open a new folder, I have them stored in the shared training Copernicus Roadshow land subsidence, and I put them in here in the original folder. So what do we do now is we start the exercise. So first of all, we open Snap, which is an InSAR software for processing mainly Sentinel images. So here, this is how it looks like. In case you're not familiar with that, here we have the Product Explorer window, and this is the View window, this big one. So the first thing we need to do is to load these products in the Product Explorer. Everything we are working with and is created appears here on the left. So we go here and we select the first product and we drag it and drop it here in the Product Explorer. And then we repeat also the same for the second one. Okay. So if we expand the product, we can see that here there are some folders. if we expand the bands, here you can see the intensity IW1, IW2 and IW3. By double clicking on each one, you can see that it's creating an image for each one, and they will be visualized here on this view window. Also, here down you have the navigation window, that it is actually showing you the product. What you see in here, you also see it here. You have the color manipulation tab. You can add many tabs, and here you have the world map, where you have the location of the product in the globe. So if you go here and you zoom in, you can see that both our products are located on the same area. Okay, so here we can see that all the bands have been opened, and what we can do is, if we are in the navigation tab, we can go here and select these two options so that we synchronize the views. So here we have the three tabs. If we go to window tile horizontally, and then we come down here to the left and we click zoom all, we can see all of them in parallel. This is the 1, the 2 and the 3. Mexico City is located here in the IW3 between the bursts 3 and 5. So okay, this was just to show you. Now before I close them, I would like to mention something. So if we focus only on this one, you can see here that these are the bursts, these parts, and in between of them there are those black parts. This is the step that is named deburst, where we actually select during the split which of them we want to process. So if we select 3, 4 and 5, this area, this black area, will be removed and the image will look continuous, because both bursts, the one and the other one, they contain on the edges the same information. So during the processing, this comes and it actually removes this black part. Okay, so I close it. So now we go to tools and we go to graph builder to build our first graph. So this is the area that we add all the operators, and down here this is where we have a tab that corresponds to each one of the operators we have up here. As you can see, we are now in the read one. It is selected, and if I click on the right, we moved to the right one. So in order not to have this error, this graph is incomplete, every time you want to create a graph, just go right-click on the right operator and delete it. So now let's build a graph. We have the read operator, so here we ask it to read the first product. And the first thing we want to do is to split it, because we don't need all of it. So we go right-click, add, reader, Sentinel-1 tops, and we select tops are split. We put it here and we just here touch the right edge of read operator. You see an arrow is being created, so then we drag it towards the tops are split. You see here that this tab has some options. We have two options, either to set immediately the parameters in our tabs or just create it. Don't insert them now, and once we will open the batch processing tool, which is coming afterwards, to set it up there. I will set them now to make it a bit simpler. So as we said, our area belongs to the subswath IW3, so this is what we select, and the area is over the burst 3 to 5. So we click on this arrow and we move it. Here, if you go to the right, you can zoom in and you can see how it looks like. That this is the area that covers Mexico City. In case you don't know in which one your area belongs, you can go to zoom and you can try to see if you select the different swaths, how they move like. Okay, the next operator that we said we will add is the apply orbits. So we just go here, we right click, add radar, and apply orbit file. We put it here, and we also connect it to the previous operator. The only thing that you can do in this tab that is created is to select the option do not fail if new orbit file is not found. This is mainly for products that are very new, and the updated orbit files are not yet available. But in this case the products are old, so there is no problem. In case you use a longer processing chain, if the orbit files are not available, then the whole processing afterwards will fail and we will not have the results we want. And the last one we do is we go to add input output and we add the right operator we have. Okay, so we connect it. So here if we go to this tab, you see that the product has a suffix at the end. It's called orb from orbits. It's automatically created. And here in the directory, you can click in these three dots and navigate where you want to store them. And then you click select. I have selected this path. And also this graph that you have created, you can click on save. Also select how you want, where you want to store it, and give it a name. This one I have already saved it as a pre-processed graph. So you click save and you save it. That's all you need to do for now. So this one, we close it. And then we open the next tool, which is tool batch processing. So actually here what we're going to do is to apply those steps that we created in the processing chain in both products. With one click, the process will be repeated for both products. If you have 3, 4, 5, as many as you have, this is the advantage of batch processing, that it applies the same processing chain to multiple products. The first thing we would like to do, since we want to apply it to both products, is to deselect this option, this keep source product name. And once we deselect it, we go here on the add opened, we click, and you can see that the two products that are opened on the Product Explorer window are added here. We just click update. So here you have all information, the track, the orbit, the type, everything. Once we have the products in here, we will go now and we will load the graph we have created, which is called a pre-processed graph, and we click OK. So here you can see that all the other operators we had created before are added here as tabs. So if you remember, we had saved the options of the subswath and the bursts, the apply orbit file, and also the write. So once we click run, the products will be created and they will appear immediately automatically on the Product Explorer window. I will not run it now to save some time. So I will just load them. I have them already processed. So if I expand now, the number 3 corresponds to number 1. I can see the differences. So the first product used to have all three subswaths, and after applying this step, we can see that it contains only the one that we need. The second happens also for the second product. So if we just click on both of them and we go to Window, Tile horizontally, we can just see that our area has been limited. Okay, now that we have completed this step, we will continue to the next one. Let me close them again. So now for the next processing chain, we will open again a graph builder. Let me expand it a bit because we will add a few operators. As we said again, we delete the right operator. And what we want to do is to co-register the two images and continue with the rest of the steps. In order to do that, we need both products that have the updated orbit files and that contain only the area of study that we want. So the first thing we do, we right-click and we add input-output read. So we add a second read operator. So here on the first one, we select the first product, and on read 2 we select the second product. The next we will do is to add the back geocoding operator. So we go to add radar, co-registration, Sentinel-1 tops co-registration, back geocoding. And to this one we connect both of the read operators, first the one and then the other one. And here in the tab you can select the digital elevation model you want, depends on the area you are. SRTM has good coverage between -60 and +60 degrees. So here we want to use the SRTM 1 second. We can leave the rest parameters as they are by default. And in case you're working over an area that there is some water around, some sea, you can have this option that says mask out areas with no elevation, so they are not included. The next one is to add the enhanced spectral diversity. So we go here, add, radar, co-registration, Sentinel-1 tops co-registration, enhanced spectral diversity. We also have it here, and we connect it to the back geocoding. And in here we can see that there are some parameters, which we leave them as they are by default. After we have co-registered the two products, it is time now to create the interferogram. So we go to add, radar, interferometric, products, interferogram. We put it here and we connect it. And here we have the interferogram. Again, we don't touch anything. Once we have also done this step, it is time to remove the black parts between the bursts that we have selected. So we go to add, radar, Sentinel-1 tops, and we select tops are deburst. We connect it, and here you can see the available polarization. And finally, we just right-click and we add the right operator, input, output, right. Okay. And in the corresponding tab, you can see that also the stack, IFG, and deb suffixes have been added. Again, you select the directory. You can save again the graph with the name you want. Here I have it saved as process graph 1. You save it, and then you click run. So let me show you the result of this one. It is this product. And if we expand here, you see that it contains intensity of both products, the 6th of June and the 10th of September. So if I open it, here is what you see. And you can see that the black parts between the bursts are not anymore here. Also, we have the phase. So this is it, and the coherence. So these are the bands that we have after registering those products. I can now close them again, those views, so that we continue to the third graph builder. So we go again, Tools, Graph Builder. Let me delete this one. As read operator now, we select the last product created. As you can see, I have shortened a bit the name before, so that you don't have to carry all that long name which is created by default. So the first thing we want to do is to apply the topographic face removal operator, because there is some extra face due to topography. So we go to Add, Radar, Interferometric, Products, Topo face removal, and we add it here. And we connect it. And in the tab, remember you select again the same digital elevation model we used before, the SRTM1 second. And here you can also select if you want to output the topographic face band, so that you have this band created in your next product. This is optional. Then we will continue to the multi-look step. So we go Add, Radar Multi-looking, here. We add the multi-look, we connect it. And this is to obtain, as I said, square pixels. So here you can see these are the source bands. We need to have square pixel. Here you see these values. So here I go and I select 8. And we have the mean square pixel is around 27. For this one, we will give you some extra information of what does this mean and why we would like our square pixels to be around this number. Okay, once we've set this one, we continue to the next one because we want to filter the face. So we go to Add, Radar, Interferometric, Filtering, Goldstein Phase Filtering. This is the filter we will use for the face. So let's connect the operator again. And in the corresponding tab, we just go to the size here of the filter and we enhance it a bit and we make it 128. The next one is to create the snafu export part. Because we need actually to make two of them. The first one is to create the right operator so that this product is being saved. And the second one is to create the snafu export one so that we will go and we will unwrap the face. So first we put the right one and we connect it. And here you can see immediately the name. And then we go and we add the snafu export one, Add Radar, Interferometric, Unwrapping, snafu export, and we add here. And we also connect the previous operator. So if we go here, we see target folder. We have to specify that. And how do we specify that? We click here, we navigate to the path we want it to be stored. So in this case, it is shared, training, Copernicus Roadshow, LAD Subsidence. I go into the processing and I write the file that I want to be created so that everything will be stored there. So in this case, I write snafu, I select it, and here you can see that the snafu is being created. So here you come and you select this option, the default option. Here you select MCF. Number of tile rows, you select 1. Of tile columns, 1. This means that it will rate it 1 by 1, not 10 by 10. Row of overlap, 0. And also here 0. To all of them. So once we have this ready, you can see that there is no error. We can save again this graph. So if you go here, save, I have it saved as process graph 2, you click save and you run it. So let me close it. So from this one we have two outputs. The first output, it is this one that contains this information. So here the difference from the previous product is that you can see that the top face band has been added. And if we open the face one, we see that now it is multi-looked, it's like square pixels, while in the previous one, if we open the face, we have it in this format. So this is not the only output we have created, as we said before. The other output we have created is here in the SNAFU folder. It also has the same name, but it is created in the SNAFU folder. We go here, we open it, and in order to unwrap the face, we right-click here and we select Open Terminal here. When we do that, we can see here the path that it is created in the terminal. The only thing we need to do now is we go to this SNAFU conf file, we open it, we go down here to line 28 in the log file, and we insert a command and we leave a space, and we go to File, Save. The next thing we do is we go to line 7, we copy this part and we paste it into the terminal. And then we click Run and it starts creating the unwrapped face. I will not run it now. So once you have done that, we go back to Snap and we want to import that. Now back to Snap. So we go to Reader, Interferometric, Unwrapping, SNAFU import now. So here in the first one, the Read Face tab, the product we select is the last one that we have created. The second one, we go here and we click in these dots, we navigate in the SNAFU file and we load this one that contains the unwrapped face and has the HDR suffix, and we click Select. Then in the SNAFU import, just select Do Not Save Wrapped Interferogram in the target product, and on the right one you see the name, but since we don't want it to be overwritten, we just add this unwrap suffix and we click Run. Again, let me close it so that I show you the final result. It is this one. So this is the face that is unwrapped. Okay, we have done that. Now the next thing we want to do is to calculate the displacement. And how do we do it? We go to Reader, Interferometric, Products, Face to Displacement. So here you see that this is the unwrapped face, and from this one we will derive the displacement of the area. So what we do here is that we go and we select the last product, which is the unwrapped one. Here you see that the DSP suffix is being added. So you go to the Processing Parameters tab, there is nothing, and you just click Run. So let me show you the result of that. Here it is. And this is the displacement. So now, if you go here to color manipulation, you can make it look the way you prefer to understand it better. So what you can do is, for example, you can put with red color the area that is subsiding, and with blue the area that is, let's say, has an uplift. Actually, what we measure here is, with the red color that we will put, is the areas that are going away from the satellite on the second pass, and with the blue the areas that are going closer. So what you can do is you can create your own color palette. If you go here, you can remove some of the sliders that you don't need, for example. You can just remove them. And you keep, let's say, only 3 of them, for example. And you can go here and so this one is blue, this one is white, and this one is red. And this is how it looks like. So once you have created it, that is how it looks like. You go here, save color palette to text file. You navigate to the path you want, and I have named it, for example, Displacement, and you click Save and you save it. So let me go now a bit back to the default ones. So once you have it created, you can go here in the Import Color Palette from Text File. You can navigate to the path that you have saved your palette. You select it, you open it, and here you select No, because you don't want all the points to go between min and max. And here you see immediately the colors. Okay, so this is it. Now we have the displacement, but what else do we want to do? The only thing that we have not used so far, let me go in this one, is the coherence. So as we said, the coherence means how well the pixels from the master and the slave images are related. The closest to 1, the better the coherence. Here you can see that the closest to 1 values, they are referred with white color. But you can see that we have too many values with very, very low coherence, that we don't need them. So what we would like to do is to mask them, to remove them, because they are not necessary and they don't help us in visualizing the result. So before we do that, we want to terrain correct the products, as we said. So here we have everything, and we want to apply terrain correction to this product that contains the interferogram, it is multi-looked, and it is filtered. And we also want to terrain correct the displacement, which is already created after unwrapping the face. So first, we go here to Radar, Geometric, Terrain Correction, Rains Doubler Terrain Correction. Here we select first this product. You can see that TC suffix is being added. You select again the folder, the directory you want to store it. And in the processing parameters, if you leave it as it is, it will just create for everything, but alternatively, you can just go and select those for source bands, intensity, phase, top of phase, and coherence. Remember again, we select the SRTM 1 second. We leave the default methods here. And here in the pixel spacing, if you want, instead of leaving the default, you can enhance it a bit. Let's say make it 100. So here also the pixel spacing in degrees changes as well. Now you can just run it, and once you run it, you will go back to the other one, to the displacement, and you will apply the terrain correction for the displacement one. And here you can see that there is only the displacement band. Select again the proper SRTM. Again here 100, and we click run. Okay, let me show you now the results of the 2 terrain corrected products. The first one and the second one. So if I open the bands and I go here to coherence, for example, because here you can see the coherence of product number 6. So now that I have it terrain corrected, if I open it, you can see that it is geolocated in geographic coordinates. The same also happens if I expand the displacement. So here it is. Okay, now the last thing that we want to do, as we said, is to remove the low values of the coherence. But we don't only want to do that, we also want to have an optical result of how it looks like if we remove those low coherence values and we keep the coherence as a background. And we also put on the top of them the displacement. How will it look like? As you see, the coherence belongs to one product and the displacement to another one. So the only way to process them is to create a product that will contain the information of both. In order to do that, what do? We need to create a stack that will be consisted of those two products. So just let me close all those open views because we don't need them. Okay. And now we go to Radar, co-registration, stack tools, create stack. And here we need also to add those two terrain corrected products that we have, only those two, nothing else. We can go here and we can open them one by one by navigating to the proper folder, but we can also do the other simple step, just add all of them and remove all the previews that are opened in the Product Explorer window and keep here only those two that we need. Again, we refresh. We go to create stack. Here you see which is the master one. Resampling type, you leave it as none. Initial offset method, we select product geolocation. In the right one, you see that the stack one has been added and you just click run. So if I open it now, this product, if I load it and expand it, you can see that it contains also the displacement band. So it contains all the previous four plus this one. The last one I will explain you right away what it is. So here we have the coherence mask, the coherence band, sorry, and here we have the displacement. So this is the output and how the final result we want from this processing. And how can we create that? We just go on the product, we right click and we go band maths. We name it as we wish. In this case, I name it displacement mask. We go to edit expression and here we need to set the following. So if you remember, when we were in the coherence, we had very low values that were corresponding to less than 0.4 coherence. What we're doing now is the following. We go and we write the following expression. If the coherence, and we select the coherence band we have here. So if the coherence has values which are lower or equal to 0.4, then we want no data value. Else, whatever is not like that, we want it to use the displacement, and we select the displacement, the original one. Here you can see that there is no error in our expression. So once we click OK and OK, the band will be created. I have it created already for you. So I just go here, displacement mask, and I open it. And this is how it looks like. If you remember, this is the final result. So this is the city. You can see the parts with red are those that are subsiding the most. So how do we have this result? I went here in the import color palette, and I imported the displacement one. I clicked no, and this is how it looks like. So this was all for how to see when an area is subsiding. Once you have created everything here, the next step that you need to do is to export those products, as we said, so that you will be able to use them in QGIS or Google Earth. I will show you very quickly how you can do that. You can select first the product you want to export. You go File, Export, and here you have options to select. If you want, for example, to export it as GeoTIFF, you can go here in the subset, in the band subset, and you can select which of all of them you want to export. It's advisable to export them one by one every time. So if I want to export the view that we have here, I select only the displacement mask. I click OK, and this is created. I select, of course, again here the path that I want it to be stored. Okay, and if I want to save it as a KMZ, this view, either I open the view here, I go right click, export view as Google Earth KMZ, or I just go to File, Export, Other, View as Google Earth KMZ. You can name it however you like, and you just click Save. Okay, now I have saved everything I need, but I need to download it to my local machine, just to let you know that the Google Earth is not supported in the RUS VMs. So you need to download the outputs. How do we do that? We select in our keyboard Control, Alt and Shift, and you can see that here this window opens, this window appears. Then you just go and you navigate in the part that you have stored your data. For example, this is my path. And this is the displacement mask, the KMZ I want to download. You just double click on it, and immediately you see that the download starts. To close this window, you just go again, Control, Alt and Shift. So this is it. Let me show you now how it looks like, this view on Google Earth. Okay, so I have it opened here, and here you can see that the displacement mask we have created, it is located like that over the globe. You can add many more bands if you want, if you export them, but here you can see that there is a problem in Mexico City. If you want, you can process more recent data, not only those from 2016, and you can see how does it evolve. How does the subsidence continue to affect this area? Okay, finally, let me go back to the presentation so that we finish with the take-home message. So, as we said, with the new Sentinel satellites, the Sentinel in satellite remote sensing is no longer data availability, but rather how to store and process all this information. In addition to that, it is necessary to explain how the data can be used and support users in their applications. And the RUS service is here to solve those problems by providing virtual machines to store and process the data, and by offering the dedicated help desk support team for remote sensing experts to help you in the projects with Sentinel data. So now, before moving to the Q&A session, let me tell you again that you can repeat this exercise by your own if you want to practice. This was all from my side for now. You can contact us here, as you can see. And now I will give you a couple of minutes to post your questions, and I will be back to you in a while for the Q&A live session. Thank you. Thank you all for attending. The Q&A document will be available afterwards. I would also like to thank again Martijn for attending. Martijn, thank you very much. Please let us know if you want to say to add something more. Feel free.
Yeah, thank you. Yeah, I'm very glad that we could collaborate in this workshop. Looking forward to future collaboration. And well, I think the levels of questions was very interesting and tells something about the knowledge level of the audience. And yeah, I would like to learn from it how many of these information products can be developed to products who are addressing the societal challenges we all face. Thank you very much. Bye-bye.
Thank you very much. And so everyone, till the next time we will meet again, try to stay home and stay safe. Bye-bye.